in your screen. And then from the RGIK office, we have a few news or information for you. The first one I want to mention, probably most of you received an email yesterday about the RGIK Executive Committee. So we just remind you that please, if you are interested in the community, get to know us by email about the executive committee, the committee that needs to be elected soon. And for that, we need candidates. And the second information is that we have 2 rock glacier sessions in ICOP, and the deadline for after is ending soon in the 8th of December. And we have another session in EGU in Vienna for also next year, and the call for abstract is ending in 10th of January. And finally, the last information is about for the next semester, we are continuing the RGIK seminars, and we have a space for 2 more presenters. So if you want to present your work, please contact me or us with a title, and we can book you a rock glacier seminar session. Okay, so today, it's a pleasure to have Lea Schmid, a master candidate from the University of Fribourg, here, a colleague of us, working on InSAR kinematics in the Swiss Alps. So I think you have a 15 to 20 minutes presentation, and then we have a 5 to 10 minutes of discussion. So it's a pleasure for me to have Lea today, and the floor is yours. And thank you again for accepting giving your presentation.
Yeah. Wait, I hope you can see my screen. Does it work? Hope so.
Sure.
Yeah. Yeah. Perfect. So great. So yeah, thank you, Seba, for the welcome. As you said, I'm a master candidate. I actually just submitted the first version today, and my master thesis is about extracting RGIK time series from InSAR, initial displacement time series. I'm doing this based on some rock glaciers in the Swiss Alps. And just so before I start, I'd like to acknowledge support by Nina Jones and Tatsu Strozzi from Gamma Remote Sensing, and my supervisors, Renaud Deloy, Lynn Rouillet, and the third unofficial supervisor, Cécile Bellet, here in Fribourg. So first of all, what is RGV? And I hope you all know that RGV, or rock glacier velocity, was included as a new parameter of the Central Climate Variable permafrost in 2022. And it's defined as a time series of analyzed surface velocity values expressed in meters per year and measured, computed on a rock glacier unit or part of it. So it says we need analyzed surface velocity values, and these should be computed on a rock glacier. Up until now, we have many studies which are based on terrestrial and geodetic measurements and also photogrammetry, but these are only in selected places, as you can see in this figure here, which is taken from the BAMS report. And especially it's important to note that the photogrammic time series, which are here shown for the Andes and for the Central Asia, are often multi-annual, so not annual. And the in situ measurements have the problem that I guess most of you know it's not feasible to do them at a large scale because we need to go inside and need to actually do the measurements there. So then there's a new technique basically, which is InSAR, which is a new one, but it's since we have Sentinel-1 data, which is has a temporal resolution of 6 to 12 days, we have regular data. And there was a first study in 2020 by Tatsu Strozzi and others who showed that it's possible to extract a time series from rock glaciers. And this is based on signal points, and you can see an example of it here. But I said before, we need to analyze time series, and we need to preferably from multiple, we need them from multiple points. So basically we need multiple points and analyze time series. And the idea would be at the end to have something like this, which is a RGV time series from the Gemi rock glacier based on GPS measurements. And so this is what we're going to go. And this is basically what I try to develop a method on how to do this based on, which is what I did in my master thesis. So before we get to the method, just quickly, what is InSAR? I'm not sure if all of you here are familiar with the concept. InSAR is synthetic aperture radar interferometry, and it makes use of a SAR, which is a radar, which is mounted on a satellite, and this orbits the Earth regularly. And each time it orbits the Earth, it sends out a signal and receives a signal. And this signal is basically in a sinusoidal wave. And between each acquisition, the ground moves, and this causes a difference in the phase, which causes basically this phase shift here. And we can make use of this to actually then compute interferograms. And these measure the ground displacement. And here, I hope you see my mouse. This is rock glacier, and therefore we can actually detect movement in periglacial terrain. Next, what is RGV, which is the second part of the theoretical background. This figure is taken from the practical concepts from the RGIK, from the action group. I encourage you all to take a look at them once to see what we propose here as what an RGV is. And as you can see, the figure is very complex. I've shown the complex one on purpose to show you that it's not just producing one time series. We actually need to temporally and spatially aggregate time series, which is the most important point, and also then cluster time series to get this spatial aggregation. So this is basically the thing we want to do. And I'm going to show you just afterwards how I propose to do it for InSAR. So first of all, what kind of study sites I used? I used 4 rock glaciers in the Swiss Alps, which are, first of all, this one rock glacier here. Then we have Steintelli rock glacier here, Brou, and Big de Bosso, or Réchy for most of you maybe know the other name. So these are the 4 rock glaciers I used. I have GPS data for almost all of them, and this is why I chose them, and also due to the orientation and just because we know the sites. So the data, I only used Extension-1 data between 2015 and 2022. In a 6-day temporal baseline between 2017 and 2021 for the sites Bec de Bosson, Distelhorn, and Steintelli. And for the last site, Brou, I used a 12-day temporal baseline, so creating a time series between 2015 and 2022. Extension-1 data, for those who don't know yet, it's C-band and has 5.8 centimeter wavelength, and the detection limit is about 1.7 meters per year in a 6-day configuration and 0.9 meters per year in a 12-day configuration. You can have higher time series, but these are often these often then cause more wrapping errors and more problems. To validate my approach, I use in situ validation data. First of all, either annual DGNS data from Bec de Bosso and Brou, although for Brou I don't have measurements for the last 2 years because we just started the time series in 2020. And for the other 2 sites, I used permanent GNSS data, which I analyzed. And this is for Steintelli and Distelhorn, although for Distelhorn, the data was only available for the first 3 years. So I have some measurements to compare it. Next, my method. So this is a bit complicated. I'm going to explain each step a bit more in detail. So the first part is to, of course, produce interferograms and unwrap these. And then I use these unwrapped interferograms. So I use a stack of interferograms for each year between July and October. And I kind of apply a multi-temporal baseline interstacking, which gives me these line of sight velocity maps. And then I get one line of sight velocity map for each year. And in this step here, I basically already performed a temporal aggregation from one single image or multiple single images to an analyzed value, which of course, in this case, is just a summer displacement, but we use it as an analyzed value. And then from this line of sight velocity map, I created a point grid in parallel, which basically consists of all pixels on rock glacier. And this is then used to extract raw line of sight velocity time series. And then I apply this the RGB processing, which I'm going to explain a bit more in detail based on the results I'm going to show. And in the end, I get one final RGB product. So yeah, as I mentioned, the first result are the raw line of sight velocity time series. Here I'm showing the data for Bec de Bosso rock glacier. As you can see, there's a lot of data, a lot of time series, about over 900. And first of all, we need to filter out the uncertainty and cluster time series. And after filtering out the uncertainty, which we put at 0.4 meters per year, and clustering time series, we get this image here. And this is my final RGV for Bec de Bosson Rock Glacier. This is based on the 2 clusters with the most time series, and it's applied. These clusters are generated using a hierarchical clustering of Ward's minimum variance method. And basically, we show that there is an acceleration of the rock glacier between 2017 and 2020. And although we can see there's still some outliers. So yeah. And if you compare the relative change of this RGV product to what we found from what, for instance, I think Permos found for the in situ measurements, we see that the trend is pretty similar. We have 2 deviations in 2017 and 2020, which are both extremes, in which the extremes are more pronounced for the InSAR time series. But in general, we can say that these trends match. And yeah, and if we look at all time series together, here are the 2 plots which summarizes all the time series which I created or extracted, and we can clearly see that Distelhorn and Bec de Bosson are the 2 fast-moving rock glaciers, faster-moving rock glaciers. Steintelli is somewhere in between, and then we have one slow-moving rock glacier, which is Bru, which is also the longest time series. And in this case, the average is based on all 4 rock glaciers, but it's just, yeah, it's an average. If we then compare the relative change of the annual line of sight velocities, we see that basically 3 rock glaciers behave the same way. And I just used the average for those 3 rock glaciers. I did not use, I did not include Steintelli, which you can clearly see has a clear deviation from the other 3 time series. Now, if we compare this relative change of the annual line of sight velocity to what we found from what, for instance, Permos, which is a Swiss permafrost monitoring network, has found, and if you just look at this part here, we see that the curve looks basically pretty much similar. So what was already found at Bec de Bosson is confirmed once again here. Basically, we showed it's possible that these the InSAR RGV matches the Permos trend, which is very nice and also confirms a bit the suitability of this method. So just just now, what are the advantages and limitations of this approach? First of all, by applying this multi-temporal baseline InSAR stacking, we reduce atmospheric artifacts, and this also reduces the effects of a single interferogram by using many images. So for instance, if I have an interferogram which is faulty, the effect can be reduced. However, it's important to note that if there's an unwrapping error on multiple images, this one is then also persistent and actually stays in the final line of sight velocity map. It's efficient to extract time series over the whole rock glacier because we just use 5 images to extract the time series. And this RGV is based on the entire rock glacier. However, we have certain limitations, and besides the normal InSAR constraints, such as orientation and only being able to extract images in summer, the main ones which apply to this method are mainly unwrapping errors, which influence final RGV. I have not shown it here, but in certain rock glaciers, I think for Bru, there is a strong one in 2020, which dampens the final RGV. And also, my observed maximum detection limit is about 1 meter per year for 6 days instead of 1.7 meters per year. I found this out due to wrapping errors already occurring at 1 meter per year, which is about a bit more than half a phase, half a fringe cycle in areas where we know that, yeah, basically the velocities from GPS measurements are more than 1 meter per year. Another limitation is the orientation of a rock glacier. If it's not aligned approximately with line of sight, the velocities are a bit underestimated and lowered. And the last limitation is that basically my images only covered July to October. So basically what we have here is just a summer velocity and not exactly an actual annual velocity, but this is a point which needs to be further discussed because it's not feasible to have annual velocity products, annual products from InSAR which cover the whole year due to the snow, to the influence of the snow cover. To sum up, I'm presenting one of the first studies for InSAR RGIK time series, and we show that these time series are comparable to GNSS time series, especially the relative changes and the trends. InSAR is able to provide consistent RGB time series without requiring in situ measurements, so it's possible to generate them also for rock glacier in remote areas. We still have certain limitations which need to be further tested, but nevertheless, it's possible to provide a complete spatial coverage of rock glacier. And just a quick outlook on what will happen next. So the next idea is to systematically apply this method on more sites in different mountain ranges, which I will mostly be working on in the next year together with gamma remote sensing. First of all, I'm trying to focus on sites which are more suitable for a 12-day baseline, so slower moving sites, just because we have, up until now at least, if we include 2023, 9 years of data. There's also going to be further research on how to exploit the RGV for climate research, and it's important to note that if you want to accurately say something about the climate, we need a large data set, and InSAR can provide that. The last thing which could be applied in future is alternative satellite data, such as SALCOM, which is already launched, which is an L-band, has an 8-day repeat interval and the X limit of about 4 meters per year, if I'm correct. And it was launched 2020, so we should have about 3 years of data now. Then we have 2 new satellites, which should be launched in 2024. First of all, InSAR, who has an S-band, but which is not really interesting for us, but mostly the interesting thing is the L-band, which has 12-day repeat interval and will be launched next year by NASA. And ESA also said that they're going to launch the Sentinel-1C and 1D satellites to replace the old 1A and the 1B, which unfortunately broke down. So this should restore the old 6-day repeat interval, which would be also nice. But yeah, these are just presumed launch dates and they're not confirmed yet. But I guess including alternative satellite data in the future would definitely be tested by us. So yeah, I hope you were able to learn something, and thank you for your attention. If you have any questions, I'm happy to answer them. As Seb already said, I've already said, I just submitted the first version today, and the final version of my master thesis will be available upon request at the end in about March 2024. And if you would like to read it, you can contact me. So yeah, thank you very much, and I'm happy to hear for questions.
Thank you, Lea, for that amazing presentation. So now the floor is open for questions. Either you can write it on the chat, I can read them out, or just raise your hand and can unlock you and you can talk. Any questions from the public? Any question? Hard. Yeah. Hanne.
Yes, thank you, Lea, for your nice presentation. I have maybe one question, but I'm also a complete InSAR rookie, so I don't know anything about this method, but I wonder how well InSAR can capture very fast-moving rock glaciers. So is this a problem, or can InSAR deal with this as well?
A lot depends on basically 2 factors. First of all, the repeat interval. So how short is the time between the acquisitions of satellites? So if we have, for instance, 1 day, then it would be possible to measure this displacement already. But the other factor is the wavelength. So the larger the wavelength, the more movement can be detected. So for instance, if we have an L band and a 1 day, we can detect up to, I think, about 10 centimeters of movement in 1 day. So basically, it depends. It's more on the technical constraints. I think there were studies which have shown in the past, which have worked with 1-day data, which have actually been able to show ability to kind of measure fast rock glaciers, such as I think Sarmin and all the rock glaciers which we have in the Swiss Alps. But maybe Tazio can elaborate a bit more on this. But so yeah, this is basically what constrains it and not the rock glaciers.
Okay, thank you.
We have a question from Moses Chunga. I can read it out for you, Lea. He say, hi, thanks for your presentation. I want to ask, what software do you use for InSAR generation?
We use the Gamma software because we work together with Gamma, which unfortunately is not open access, but there are also open access software such as Snap, and I've not tested these yet, but the idea would be maybe to test them if they work to see if we can also kind of extract time series and interferograms with other softwares. Yeah. Thanks.
Related question from Mariano Brito. Says hi from your presentation, and then what software are you using? You already, and then if it is the same software for the stack analysis areas.
Yeah. So basically, up until the time series, I produce everything in almost everything in the Gamma software. So creating the interferograms, unwrapping them, stacking them, and then also extracting the time series. The point, yeah, that's also they also kind of extracted with the Gamma software, but afterwards the processing is done in Python. But yeah, it's just important to note. I would like to test other softwares in the course of the next year to see if we can provide some kind of open access, easy tool for which is also applicable without having any software. So yeah. Yeah, by the way, that will be quite helpful. And we have a question in the chat as well from Florian. Lea, thanks for your awesome presentation. Did you have to deal with radar shadows? How did you tackle that issue? So I did not really deal with have these issues because I chose the rock glaciers on purpose in areas where we know they're suitable. For instance, 2 rock glaciers, they don't really have a large, actually one has one, but the tile slope is not that big of an issue. And yeah, and the other 2 rock glaciers, yeah, they're also not an issue. So we have it, but yeah, I chose the rock glaciers on purpose where I knew that it should be good for radar geometry. Thanks. We have another question in the chat. It's getting quite active. There's Moradi Hoda. Say, thanks for the nice presentation. How important is to have data during winter? Or do you think there will be some changes in rock glacier velocity during winter time? So we know that the movement consists of, summer, there's a summer and a winter displacement component. If we have, the majority of movement, as far as I know, occurs in summer, but there's still a part which occurs during the winter measurements. So, and usually the velocity there is also slower, but we have displacement which occurs. So it would be important to have, of course, the whole component, but with InSAR, it's frankly not possible. So we have to deal with these limitations and find a way in how to kind of, how to treat these limitations. Yeah. Thanks. We have a question from, I don't see who it is. Lynn.
But
Lynn.
it's not a question, it's just about this. So in terms of absolute velocity, if you discard winter months, which is, as Lea said, there is no way around this in InSAR. It doesn't work on snow. It's in the absolute velocity is maybe overestimated, but when looking at relative trends, that's the point of doing of generating RGB. It's not an issue as long as you keep a consistent time observation window, and that's what Lea did in this work. So keeping July, October, I believe, each year, and then you basically compare how it changed between these seasons. And of course, if you would have the entire year, you would have different absolute values, but maybe the trend would be similar.
Thanks. So that was clarification from your part. I think Cecil has.
Yep.
She raised her hand.
Yeah, I have one question. So we talk now about temporal scale. What about spatial scale? So now you selected a few time series from your whole 900 points. And I was wondering, is there like a spatial area where they are all concentrated, or is it like randomly distributed over the rock glacier? Is it different from one rock glacier to the next? Maybe say a few words about that.
Thank you for the good question. So on the Rechi, sorry, Bec de Bonson, it's actually interesting because they're all concentrated. So Rechi just consists of two lobes which are parallel to each other, and in my case, I have basically almost all time series which I end up at the end of the clustering are located on the upper lobe or on lobe 2, which is the larger one, which is interesting, which is not that consistent with GPS measurements. But it's mainly due to because, especially on the other lobe, there's a fast-moving area which leads to an environment wrapping error in almost every interferogram. And on the other rock glaciers, so Bru has a very good spatial coverage on the whole rock glacier. Distelhorn, there's the middle part which moves slower, which there's GPS there which shows that it does in fact move rather slow. So that part is not included, but the two fast-moving parts at the front and at the roots are included. And Steintelli, that is a bit my issue there. There's just a small part of the rock glacier which is used at the end, and this is not that in accordance with the GPS measurements. So here there are some issues, but I've found some reasons such as the orientation of rock glacier, which is for Steintelli, it's not exactly oriented in line of sight. But yeah, so it depends on the rock glacier, but usually the measurements, they kind of, I compare them with our GPS maps, which we create, our surface velocity maps, and they mostly fit very well.
Thank you. Do we have more questions for Lea? If you want, please raise your hand or write it on the chat. Do we have Jan? She says, "Hi Lea, nice presentation. Sorry for not being able to use my camera or my microphone right now. I'm wondering if the 4 rock glaciers have more than one moving area. How did you deal with the spatial heterogeneity?"
Thank you, Jan, for your question. Russia has multiple moving, Bec de Bonson has multiple moving areas, and there we know from our GPS measurements that the movement is rather heterogeneous, and there's kind of a disparity because basically my time series are interpolated over 25 times 25 meter pixel, whereas our GPS measurements are point-based. And I also believe that basically the spatial heterogeneity is partially responsible for maybe that only one lobe is used on Bec de Bonson rock glacier. And in another case, because I used the whole rock glacier, I just then clustered the time series according to their behaviors. And so, yeah, for instance, in Distelhorn, there are multiple moving areas which are considered for the final RGV. But it's important to note that this one has a very homogeneous, basically a very interesting moving behavior. So we have a small, fast-moving part at the front, then a slow-moving middle part, and then the fast-moving part at the root. And this seems to work very well for my method. So yeah, it depends very on the rock glacier.
Lynn?
Yeah, it's just a comment because a bit along the same line than my previous one, actually. The nice part with this method is that it's not a big deal in a way if you have spatial heterogeneities in terms of absolute velocities. And that's why the clustering is applied in terms of trend of behavior, as Lea just explained. Then you focus on finding the main pattern in terms of relative velocity. And you can have a rock glacier that have several a big range of velocities, as also Lea showed in this graph, where you see all these lines over the rock glacier, but then you focus on discarding what is not following the general trend, typically some blocks at the front that are behaving differently, and discarding that and keep what is expected to be the main pattern for this rock glacier relatively, how it changed from a year to another, basically. And yeah, Cecilia maybe will complement.
No, it was just maybe a follow-up question on this again. Sorry, I'm very interested in the RGV time series, and you said you filtered out. So you said you had this threshold limit for velocity, that you filtered out all these points with below this threshold. What other type of filtering are you actually applying on your data? Is it the only one, or are you sort of looking for statistical outliers other than in terms of limits or range or this kind of, yeah?
Yeah, so in fact, this is actually the only filter which I ended up applying, which is, yeah, it's based on a bit like the uncertainty of InSAR. And I experimented about with multiple statistical tests, or like with the mean plus minus standard deviation. But in the end, I found out that if we just apply the clustering and then filter out kind of based on the cluster with the most the most time series, this provides us with with pretty good results. So I kind of refrained from using any more clustering, also because it was hard, any more filtering, also because it was hard to kind of justify that, and it removed points which were actually not that bad. For instance, if you have a very strong acceleration and use a standard deviation filter, you can't really see this then. So that's basically a bit the reason why I just used the clustering plus, of course, the first uncertainty filter.
We have another question for Marije.
Yes, hi, thanks for the nice presentation. Coming back to an earlier point, you said that you specifically chose the rock glacier so you don't have any influence from shadows on the processing, and also for the line of sight, if I understood it correctly. Are you planning to also try this method for where you possibly have more effect of the shadows, that you can see how well your method works?
Thanks for the question. So first of all, yeah, I have some issues with line of sight on Steintail. So I already have this, I already kind of have this issue, but I would definitely also like to try it on rock glaciers, which, yeah, are a bit like less suited, just to see if there are also other kind of potential sources of error, or how can we deal with these errors, because, yeah, it should be possible to kind of apply it on multiple other rock glaciers and not just kind of on ideal cases. So yeah, so definitely, that's definitely also an idea to kind of examine in the future.
Okay, thank you.
We have another question from Nina.
Hi. Thanks, Lea. You can hear me?
Yes, I can hear you.
Yeah, sorry. Back to the filtering. So you filtered based on uncertainty, and in your presentation you mentioned something about 0.4 meters per year. Can you just explain again why this value and how you determine an uncertainty to filter out points based on a rate?
Yeah, so basically this value of 0.4 or 0.2 for 12 days is taken from the paper by Tatsu. I think it's, yeah, somewhere in discussion they kind of say it's about uncertainty of 2 to 3 meters for 2 to 3 centimeters per each 6 days, which if you then multiply it up to 3 minutes, which I'm not entirely sure how much, up to like kind of a year, you get about 0.4 meters. And I kind of calculated the mean of each time series and just filtered out all time series which were below a mean, which had a mean below 0.4 meters per year. So yeah, that's what I did. But I'm not entirely convinced about this filter, and I have 1 or 2 ideas on maybe how we can maybe change this filter in the future. But I have to test those. Yeah, I have not tested them yet.
Okay, thanks.
Well, I think, do we have a very last question for Lea? We can keep going. Any other question for Lea, either on the chat or on the room? Michelle. Okay. Yeah, this is a general question. It's not for Lea, but it's just more a side of a question about the EGU AGM 2024. But this is a very crucial question. Are we having a meeting with PISA party? As I said before the introduction of Lea, we have the 2 rock glacier sessions for next year that we are sponsoring. One is in UCOP in Canada, and the other one is in the EGU in Vienna. So either the teams of the organizing sessions might organize some informal dinner after the session. So keep in touch if you want to participate in one of those sessions, and then having a party pizza or party schnitzel or whatever you want. If there is not more questions to Lea, I want to thank you again, Lea, for the presentation, and all the public and the interventions for the very nice questions. The nice discussion about the topic was very nice to see the engagement of the participants. And this is just to remind you, this is the last seminar of this semester, but we are coming back the next semester, and we still have 2 places open for people. So if you want to present your topic, your rock glacier topic, no any topic, of course, you are more than welcome to contact us. And please stay in touch for more news for next year. But thank you.
Thank you.
Thanks. Ciao.
Ciao.